Okay, so I guess we're ready to start, and we'll have Youssef. Are you doing the first presentation, or it's Albert? Okay, so Youssef Ashash is going to give the first presentation. This morning we're really going to focus the first part of the morning on the Geotech Working Group on reference rock and VS. Thank you.
Good morning. Do I need to get, okay, is this good? Okay. So today we have two presentations related to the work that the Geotechnical Working Group is doing. One is on reference rock, as well as one on Kappa. The one on Kappa, Ken Campbell will be making that presentation. In my presentation, based on some requests, I will be expanding a little bit beyond just reference rock into some of the other issues that we are dealing with in the Geotechnical Working Group. Okay, so I'm going to be talking about how we're going to use the reference rock for NGA East. It's a proposal. It's some thoughts or the framework we have currently. I'll talk about the collected data, some data statistics, and I should say proposed models. There are many ways we can go forward with this, and this is something we'll talk about today. And this work actually was initially led by Walt Silva, and I'm presenting it on the behalf of the Geotechnical Group. So the use of reference rock for NGA East. It is the rock at which ground motions from simulations will be generated, and it is the reference condition from which site amplification functions will be developed. So let me explain a little bit. In the meeting we had in June, there was a discussion about having two types of rock, a simulation rock and a reference rock, and it was passed back onto the Geotechnical Working Group as to how we want to handle that and based on what we see in terms of evidence. As you will see from things we're going to talk about, we're proposing to have the same thing being reference rock and simulation rock, and the intention for us is to whereby the motions are generated at a reference rock, we will then, within the Geotechnical Working Group, will develop amplification functions for site conditions other than those for reference rock. And there's a whole process that we're going to go through within the Geotechnical Working Group to develop this amplification function or functions that would be used within the NGA East. We are going through a systematic process of data collection for the dynamic soil properties, selection of appropriate site response models, performing large-scale simulations, and then developing these type of amplification functions. We are looking at using both nonlinear and linear and equivalent linear approaches to site response analysis. So this is all within the scope of our activities. We have already started this process. We are already collecting this data, and I'll talk at the very end some of the key issues associated with the data collection for the soil columns that we are going to develop. We're going to develop generic soil columns across the eastern U.S. to develop these amplification functions. We are also going to be doing something else, and this is again in response to a request I got last night. We are looking at issues of how to estimate the VS30 at recording sites, and we are looking at, and this is to help with the work that the data group is doing. We're looking at several approaches. A preliminary approach using terrain-based models, things such as Young and Walt developed. A medium term, possibly consider the work that Mia and Somerville has developed using P-wave-based method. This is something we're still discussing within the Geotechnical Working Group. We're still looking at several alternatives, but these are things that we are looking into. We have not gotten into it at all yet. It is still under discussion within the Geotechnical Working Group. These are just simply some thoughts and some suggestions on dealing with this issue. Okay, now, how did we go about looking at our reference rock? What is the method we went for? Is we tried to find places where we had actual records of shear wave velocity and P wave velocity in reference rock, and there's, of course, in rock, hard rock, and there was also an issue of how you define that hard rock. The data set that we currently use is the work that was done for recent nuclear power plant license applications. These are very well documented, have a lot of records in them in terms of field investigation, direct measurements of VS waves, VS velocity, or interpretation from P-wave velocity measurements. And what you're looking at here is the distribution of the various locations we had. We also have some non-nuclear power plant sites, but our first focus was on those license applications because they contain the highest, what we believe is the highest quality data. We are looking at trying to collect more information in the future, and this is some of the data needs we will identify here today. So if we look at some of our typical records, and I just picked a few, we have similar plots developed for all of these sites. We still don't have, by the way, the actual numerical values of this data, but these were all plots taken out of the license applications, and we scaled them so we can read the information of them. We are in the process of acquiring the actual numerical, the digital data. So, for example, here at Bell Bend, we are looking at, you see the geologic column, the glacial material overlaying a shale. And we looked at areas whereby it appears that the velocity has become constant. And in this case here, our pick from a downhole is this number, and from a PS logging is this one. And so this was a way for us to interpret. So there was a fair amount of judgment in terms of how we define where this rock is. And this, for example, this location, it's about 200. The start of our, what we're calling this hard rock or reference rock, is at around 230 feet. This is, for example, the record at Bellefonte, and you can see that there's really very, very little soil there, and the rock is shallow, and the velocity, we had to pick there, we picked a number of around 3 kilometers per second. This is data from Beresnev and Atkinson up in Canada, and we had a bunch of that data that we used, and we consider this as data from, this is, for example, reflection survey. We don't have the actual definition of the geology yet there, and I'm sure Gail can provide us with that information as we proceed. So this is, for example, a rock that is defined at a depth of 150 feet in this case. There's a weaker rock above it, and then a shallow soil. This is Comanche Peak in Texas. We're looking at our rock at being down at a depth of around 5,000 feet. So here we're going really quite deep in our definition of where this rock is. This is via summer, and there we have fairly shallow. It's about 50 feet from the surface, and we're looking at a fairly significantly high velocities there. I think this is P-wave velocity, by the way. So we looked at both P-waves and S-waves, and I'm not showing you the entire data set that we have collected. All of that eventually will be properly documented and made public as part of our activity. So then we went ahead and started doing some statistics on this data. And the statistics we have, for example, this one are all the sites we have, and we're looking at variability within each site, looking at shear wave velocity for all these sites that we have, because we have, for example, multiple measurements of shear wave velocity at a particular power plant, for example, site, and so we would lump that to represent a data point for us. And we looked at inter-site variability and intra-site variability. This is same plot, but for P-wave velocity measurements across the site. And we present them in both scales, feet per second and meters per second. And also you're looking at the variability there. as well. We look at things such as trends. If there are any trends in terms of depth to the top of the VSREF that we are looking at. For the shear wave velocity, we really do not see much of a trend. The horizontal axis is log scale for us for that. And this is where we're trying to see if there's a bias in the way we've picked the numbers, or see if there are trends, some definitive trends. We didn't see much based on where we picked our reference rock. And then if we look at depth to top of VP, you can see maybe a little bit increasing based on our picks with depth, but really the trend is not, there's no strong trend, which makes us feel comfortable with what we have picked so far in terms of how we define this reference rock from the measurements and our estimates of it. We had to look at also issues of estimation of Poisson's ratio for that. And again, we have the arithmetic mean is close to about 0.28 based on the P wave and S wave measurements, where we have those measurements, and where we don't have, we end up using this value in our estimates to broaden the number of VS shear wave velocities we have. This is a geographic variation of the VS reference that we're looking at, and we can't really see any specific trend based on region. Why we're looking at that? Because we want to see, one of the issues we wanted to look at is that, are we going to do any regionalization of this reference rock? Are we going to select certain parts of eastern U.S. to have one reference rock and another with a certain velocity, and another site or other region with a different rock velocity? Right now, we are a bit inclined to say we don't see a clear trend in that, so the data doesn't seem to be sufficient to help us with that type of regionalization. Same thing with the P wave velocities. One could say, well, if you go a little bit east, it's a little bit different than further west. I don't think the data is sufficient to help us with that. But of course, this is all up to discussion today. We're looking at the variation of depth to top of VS, and as we would expect, further up in the northeast, it's very shallow. As we go further south, they're quite deep, because we're dealing with the Gulf Coast sediments eventually. And that is going to raise an issue for us as to where you define the reference rock down there in that lower part, this lower part here. Okay. Better even? Okay. Was I too low? Someone should have said something. Okay. Okay. You can hear me better now? Oh, wow. I hear myself too much, too well. Okay. So we have here, we're looking at issues of trends of depth to our pick of top of VSREF, and you clearly see a trend of increasing depth in this region here, in this region, and this really relates to the geology. However, we also have a lot of shallow reference rock up north in this area. It's not a strong trend, but nevertheless, there's an issue we're going to have to deal with in this region as well. Okay, this is the depth to top of VP. And again, you'll see fairly deep down here and much shallower up in this region. And we will have to decide how we're going to carry our site amplification models. And again, I will raise that issue as we do as I raise the critical issues. So here's some statistics we have done on the VS variation, and you can see it ranges anywhere between 8,000 and almost a little bit over 11,000 feet per second, sort of say 2,500 to say 3,500 meters per second. So it's a range that we have there. And if we do some statistics on this, and this is where we have the statistics of VSREF plus tau, which is intersite variation, plus sigma intrasite variation. And you can see that we are coming up with a mean or a median of about 3,000 meters per second, whether we use a normal or log normal. There's a slight difference for the distribution, but they're about the same. And one of the things we did is, and this is work that Albert did did a t-test of the EPRI 1993 recommendation, because we wanted to look at past knowledge and whether we need to change that or not. If you go strictly by the t-test evaluation of the recommendation in the EPRI 1993, 9285 feet per second, the p-value is 0.007 and technically rejects this hypothesis. So again, this is something, I'm not making any conclusions, I'm just giving you data information so that we can discuss that. It doesn't mean we are going to necessarily reject EPRI's recommendation, but it's something we want to really think about, given the data we have, how we've collected it, and whether this difference is significant enough or not. But that is an important element of what we have done so far, is that things are a little bit different. They are not a lot different, but they are different. The P-wave variation, this is the range that we have from all the data we have so far. And I will again emphasize that this is by no means a complete data set. We're hoping to get more data, say, for New York, for example, in the New York area, which we don't have a lot in that area, so maybe that might change things for us a little bit. And this is now the P-wave velocity variation, and again we did a t-test on the data for the EPRI recommendation of 16,000 feet per second, and again we end up rejecting this hypothesis. We'll have to decide again if this is how we want to go or not. And this is now the sort of various proposals then we could consider in terms of the variations, coefficient of in terms of the mean, coefficient of variation and distribution, and 5 percentile and 95 percentile, whether we have normal, log normal, and normal with covariance of 0.05. And these are the various numbers we have come up with. All of them, the mean is the same. It is the range that it covers, the lower 5% to 95% that we have for the data, and the range that we want to consider in our discussions here. And these are issues that will impact the whole project, how we are going to select, what numbers we're going to select. The question is also, do we want to just stick with the EPRI recommendation? That's why I put it up in the title up here. Do we want to stick with that? Or do we want to move to these new numbers based on the data that we have? So, let's see. I'll click on the slide. Oh, okay. So here are some critical issues. There may be some other ones. And actually, there's a few more I'm going to add right now. Critical issues is we have a range in the values for the reference rock. Is that range significant for simulation? We have an issue of how do we define and where do we define this reference rock down in the Gulf Coast, where the sediments may be several kilometers deep. In our group, we have talked about, we limited the depth of the column that we will consider in our site response to the maximum period of interest. And at that point, we will assume, even though the geology is different, it doesn't follow the geology, that this is where the reference rock is to do our site response and site amplifications. There's also a relationship between VS and Kappa, and is it sufficiently significant to also warrant that we would relate those two numbers? There's an issue of regionalization of the reference rock. Do we want to regionalize or not? Currently, we do not feel we have enough data to support regionalization, but maybe we're going to get more, or people feel differently about this issue, that feel that maybe we do need to have regionalization. In our view of, when we're doing these reference rock, so for the east, we're looking at using this hard rock as where we're going to do our hazard and then site response, and we're staying away from, say, the 760 meter per second that is used in standard in USGS maps. So we are moving, we're not going to work with a 760, we're going to be working, we believe, with this new reference rock because it is more meaningful as an impedance contrast and from a site response point of view. Data needs. Is there data elsewhere that is relevant to the central eastern U.S. that can be included in our statistics? I think we really collected a lot of data, but a lot more than what we had access to before, and we really know where the source of the data is. But I am sure there is more data out, and we would like to have see where this data is, and if the audience has suggestions, please let us know, because we want to include that information. Or if you feel some of the data we have used is somehow has some issues, please let us know as well. I think these are things we want to have. Let me ask, I have also some critical issues for the geotechnical working group. Do I talk about them now and then go into discussion, or what would you like me to do?
Let's talk about this
first, and then I'll go to the next slide.
Okay, so I think we kind of have a plan. Norm has prepared a couple things. I think that's going to be helpful in leading the discussion. Thank you for highlighting these points. We'll come back to them. I think that what Norm has is a slide that shows how the VS results. Oh, do you still have my memory stick? We could. Oh, okay. So what Norm has just prepared now to initiate the discussion, then we'll go back to Youssef's slides, is how we're going to use that VS data in NGA East, because that's going to guide some of the decisions or discussion regarding that. So I could sing and tap dance. If I could, I would. Entertain you in the meantime. And he says she can, so. Okay. Let's have the pro do that. Actually, you know what, let me do one thing here. Can I cheat and just copy this whole slide? And we'll put it on this slide. Geographic one, I think. I hope. Oh no, now I don't have the copy. Like, if you did Control V, that's why.
Okay. So first, I think we need to, in talking about what Youssef has shown, what are we going to do with the results? What do we need out of the geotech part? And there's really three things we're doing. One is our charge for NRC is to get a hard rock model. But if you want a ground motion model that's much more broadly applicable, for example, if USGS wants to do 760, we need amplification factors. So the first part is just getting amplification factors that we can use in the GMPE so we can get soil ground motions. But we also have two other parts here, and that is How are we going to correct the data that we're looking at, either for validation? So when we have our validations of our simulations, those are generally going to be models geared towards rock conditions, and we need to be able to give them amplification factors that they can apply so that we are comparing the data in the correct way. The other part then is also in the data we talked about yesterday on looking at what path effects will be, what we'll get for path effects and getting stress drops and so forth out of the eastern U.S. data. We need to be able to take the site amplification factors out of that. So part of I think the charge that was laid to your group yesterday was you've got a bunch of coordinates of stations. Tell us what the site amplification factors are. And I don't think we're there yet, but that's something we have to be able to find a way to provide information for those two steps in the modeling part. One, the validation, and then the evaluation of the empirical data. For selecting the reference rock velocity, part of this, and I think what you're talking about, are we stuck with picking a single value and we will say it shall be, I'm going to use meters per second, not feet per second, okay, 2,800 meters per second or whatever that's going to be, or right now, should we actually be having that as a parameter in our model? And I'm not sure what is really the single best way to do. I think our current plan has been a single value, right? So, and that's what Yusef was geared towards. If he has to pick a number, how is he going to pick one? If we're going the single value approach, we don't want uncertainty in that value. It is a number, and we're just simply going to use that, and everything has to be referenced off of that. But our alternative is we could have a model that could let you adjust that value depending on, I put here what the rock VS, or if we're talking VS 30 or something, it's not measured in the soil, but from the top of the rock, down 30 meters or whatever we want to be doing. So I think those are sort of the issues. If we want to just focus perhaps at the bottom, the first issue is our charge, shall we just say it is a rock model and a single value, or do we need any flexibility such that can be site-specific in terms of where you are in your particular power plant? Because otherwise, we want to tend to go to the harder sites, I think, right? And maybe that's not even the case. So we'll begin, I guess, our discussion from back to even the Geotech Working Group. And what do you see let's talk on the bottom issue. Is that a feasible thing to be looking at a range of, a dependence on shear wave velocity of rock, or is it really that we should be picking a single value?
Yeah, come over. I guess this question is going to be pretty relevant to the simulation group. That's going to impact simulations in the end, right? So I don't know. It's going to impact a lot of things, but
the simulations must be done for a single value, right? So the simulations will be done for 2,900 or be done for 2,600 meters per second. They have to be. We're going to do them all at a single value. The question being in the rock model itself, we could actually say, here's our hard rock model, yet in that is a scaling to different levels of hard rock. It's almost like building the GMP to go down to 760. Well, you could build it to go up to 3,000 or down to 2,500 or whatever it's going to be.
So in that case, we haven't talked about amplification yet, although Norm put a couple of issues here, and I guess it's not on the schedule this week, right?
We have to deal with it.
We have to deal with it, that's for sure, but we'll talk about it more. I guess, so just to put things in perspective, there are priorities with the handoff, and the VS rock was a pretty important one. So that was their first priority. I don't know if you have really started on the amplification or not, but I'll let you talk about that. But that's why I guess the sequence of things, that's the first thing. First, establish the rock. Now, when you guys are going to do the amplification, you're going to go from the rock and develop a method for the site amplification. And whether that could include that rock variation in there or a separate tangent. Okay. So, Youssef, take control.
Yes.
I'll say yes to everything. Pardon? This is an issue we haven't resolved. We are still trying to figure out within our group what it is we want to do. Do we want to just stick with the raw velocity that the simulation groups will generate, and we'll just use that as our elastic half space and then do our amplification? Because one of the other things we were thinking about is, maybe would the simulation groups be interested in running simulations for a range of rocks? But I just heard from you, no. So I have a clear no, so that answers that question. And so we'll have to decide as a group, is that something, and how are we going to do that kind of amplification from whatever, we go back now to simulation rock versus a reference rock. Our group has really wanted to avoid that separation or between simulation rock and reference rock. That's kind of the strongest feeling. So in a way, what I'm trying to say is probably we will simply, if the decision is to go with a single velocity, then we would go also with a single velocity, and our amplification functions would go from there. That's where we were heading. We have not finalized that process, because even actually the statistics that we have are fairly recent. We have not had the opportunity to talk about them. And I want to ask, is it okay I ask Walt and Ken if you'd like to comment on this issue? No?
With Walt, we have to ask him direct questions. Okay, so. For all of the sites that you've looked at, Walt, I mean, what reference velocity makes sense to be using if you look back at all of the site response studies you've been doing at the nuclear plant? And I'm going to make you come up here, otherwise.
I think actually that it's 1200. And then he's going to get up to come and argue.
I guess I'm Walt Silva. To me, it doesn't make a lot of sense to have two sets of amplification factors. One set for hard rock or semi-hard rock, and another set for soils or firm rock. And I don't see any compelling evidence to reject around 2.8 kilometers per second. I think one thing that has to be pointed out, any of these velocities that are deeper than about 100 meters are inferred velocities, shear wave. They're not measured. So they shouldn't be treated the same way statistically as measured values. So I don't know if that answers any questions, but I would prefer, or I think it's more reasonable to have one rock velocity, one Kappa value.
What value, if you were looking at all the site response studies, what value would have made sense if you had looked at this site?
At all the velocity information I've looked at for hard rock in the east, again, I don't see anything compelling to reject around 2.8. And I don't think there's much difference in site response between 2.7 and 2.8 and 2.9. The EPRI 93 work looked at that. The difference in amplification due to a difference in hard rock velocity, and it's not that big a deal, 10, 20% difference.
Sure. Quick question then. If we had more data, do you think nothing would change dramatically, is your point, right? If we had more data, we might move a little bit, but do you think that having more data would help? Just trying to focus that on the data needs. Is there data that exists that you're not aware of?
We have some additional data from some projects that, sort of proprietary data, and it doesn't depart from this very much at all. In fact, it's around 2.8, 2.6 to 3.1 kilometers per second. And I think it's important that if there's a hard rock GMPE that's developed, that should include a range of about 2.8 kilometers per second. There are instances in the east where people have done site response because they had 20 feet of concrete at 7,500 feet per second overlying 2.8 kilometers per second. That doesn't make a lot of sense to me. So a basic GMPE for hard rock in the east should be able to say it's good for this range in hard rock velocity. I think that would be real important.
Are you planning to collect data from Canada? Because all the sites that you showed were in the U.S., right?
No, we use data from Canada. Atkinson's data that I've shown, that's from Canada.
Okay, so I heard Bob Young said as well, having a model that we declare is good for a range as opposed to having people try to correct from 2,800 to 3,000 or a slight difference in rock is preferable.
Yes, this is Bob Young. I would suggest that the model we come up with should be able to deal with a hard rock velocity that has some reasonable range, and whether there's a change in the numbers that we actually include some variation due to the change in velocity, that's fine, or it's a constant value. But for applications, it's sometimes very difficult to say that we're right at 9,300 feet per second number, where and you may have to go another 3 kilometers down or 2 kilometers or whatever on your site response if you're at 8,900 feet per second rock, and that's a very thick layer. And right now in the applications, we would be doing site response for that case. We would do it. We would do it.
Getting back to Yusuf's question is of can we deal with a range, which is what Bob has just put us back to having a range. I would think that we would prefer to have the simulation still done for a single value, yet have some extra factor come from your side as to what do we need to do on to accommodate a range. So essentially there'll be an additional variability that's applied. Bob, does that fit what you're thinking? Yes. Okay. For those on the phone, he nodded yes. Okay.
Gabriel Toro, just one comment, more or less along the lines of what Bob Young said. Doesn't it make sense in this case to set up a reference rock that is high enough that it will work for all sites, and then develop a procedure as opposed to a result for how you go from that reference rock to other reference rocks? And have the recipe in place.
So That would be choosing the highest reference rock.
The highest reference rock that works at all sites.
And then a way to adjust it
and
to
then
lower.
A procedure to adjust.
Or a scale factor.
Or a scale factor. Yeah, even a scale factor or at least a recipe for how to do it.
So that's going back to having different adjustments, but I think we're getting a little bit into proponent discussions, but this is a critical issue, and I think we need to at least hear a little bit about it, because that's going to be important to guide.
But I wouldn't call these proponent discussions. So the proponents will be how you do that site response. I get to beat you down a little bit. This is really the form of the model, and what should the form of the results be? And there are really two things. When I had written on there, should we have a sort of VS, rock VS in the model, that's the same kind of idea that Gabe was just saying. Use a very hard rock and then a way to adjust it up and down to whatever the rock conditions are at your site. But if you really don't know them that accurately as well, is it better to just say we cover this range, and as long as you're in that range, you don't do anything? Do you want to respond?
That would be my preference, actually, is that you have, not that because the geotechnical working group doesn't want to take this on, but it seems to me from the GMPE and that I would be able to say this is applicable for this range, because even our knowledge is probably not that good to be able to resolve one, it cannot be just, even though we do the simulation for a single value, clearly we would have to acknowledge that it actually applies to a sum range. And if we can say we accept that this is the range, that would be one way. If we are to do the functional form that will move us from the single value simulation rock to other simulation rocks, the nature of that function, I see it to be quite different from the amplification functions that we are going to develop for the site effects. So this becomes a bit of a different animal, for the lack of a better word, and we need to think about it. Now we get into what form the model should take, but it's, would it be some sort of a frequency-dependent function or something, which also, so that there, it adds a complication, and I don't mean to propose another working group, but maybe we'll need something whereby some intersection between the couple of groups to be able to come up with this number as well. Ken, you want to say something?
Yeah, Ken Campbell. I think the idea of having a range is a very good idea for the reasons that the practitioners brought up. I mean, they're in the trenches every day. They know how this stuff is used and misused. So I think it's a very good idea. However, I don't think the geotechnical working group is the one to be able to characterize that. I think it's got to be the simulation group that tells us what kind of additional uncertainty we need to incorporate in order to say we're going to adopt this range. And the wider that range, the larger that uncertainty should be. So there's a trade-off. And so I think that that's a pass-off from the simulation group. We can use it, okay? So once we have that range, we'll factor that range also into the development of the amplification factor. But it seems to me, I mean, I don't know that we have any basis for knowing what additional uncertainty would be required in a GMPE. The simulation group obviously would be able to do that, and I know it's difficult, but maybe they could use some simple models like stochastic simulation models to get a handle on that uncertainty as opposed to the more sophisticated models.
They are very simple at that rate, Dave.
Dave Boer, just following up what Ken was saying, actually it's the path working group that has to deal with the crustal structure. Okay? And because the simulations are going to be done for different crustal structures, but I just did a simple calculation of square root and impedance thing, and between 2.6 and 3.1 is like a 10% difference in amplification. So I don't think we're going to find it really a very large effect overall.
So I think we probably will not formally ask the simulation group, but we may have a single person deal with that. These are linear amplifications. We're not dealing with a lot of complicated things, and we can set that value. Part of the issue then will be from the practitioner side, what's a reasonable range to be putting on that. But I think for moving forward right now, this is not something we'll decide today, you should be focused on a central value that makes sense. I think what Walt is saying is, if you don't have a good reason to make a change, don't make a change, okay? So we should have a compelling and significant reason for moving off of what we've done before, just so that we could compare to the old models in an easier way. Right? Any other comments on that?
No, I think this is a good way forward. I mean, of course, we'll formalize it, but yeah. As I mentioned, we internally haven't decided exactly which way we're going to recommend, and Walt has a very good point. If there is no compelling reason, why? And especially if you're going to have those linear functions, then you can easily move, and with a 10% difference, I think that will all be a wash. So.
All right.
Do you have any things you want to go back to your?
Yeah, now go back to your critical issue.
To the next one. Okay, so this is, so what we have discussed here are reference rock critical issues. Shall I ask any more comments before we move on to other things? Okay, so I will move on to the next one, which is I'm raising some additional issues based on some feedback I got last night that may be of interest to the audience. Is what are the things we're dealing with? What are the things we're going to be struggling with? And we're just starting on these issues. So our work, after we produce the reference rock and the Kappa, which Ken will be talking about shortly, is to look at these, let's call them soil amplification factors, or amplification factors from hard rock. And the way we're going to approach those, we're going to be looking at site response models, and the exact form of them we have not selected. We're going to have to develop idealized soil columns across the eastern United States representative, central and eastern, that we will use to run simulations using the ground motions generated by the simulation group. Not all the ground motions they generate, but selected subsets of their motions. And we're going to use that and temper it with empirical amplification functions, if we can find some, and then develop our amplification functions. So what are some of the issues we are identifying right now that are critical to us is what type of models will we want to use in our site response analyses to characterize this site amplification? Linear, equivalent linear, nonlinear site response models. So we have an activity within the geotechnical working group that is looking at the available models and what different people have been using, and we're going to propose how we're going to work with these. These would be the type of models from a practitioner point of view will be used whereby you will do your amplification or site response. We're also going to temper it with the issue of how deep we go into the soil column. We have not decided how far we're going to do that, so that becomes a critical issue as you move down the Gulf Coast, for example. The other issue is dynamic soil properties. In many of the site response models that we use, be it equivalent linear or nonlinear, we use modulus reduction and damping curves. The latest, for example, versions we have are, say, Darren Daly's model, for example. But many of these models do not show the data behind them. And one of our tasks is to make sure we have that data to justify those models or variations of these models. And as part of our activity, we have different individuals involved, including Ken Stokey, who has done a lot of work in this area, so that we don't just have models, we have the data behind those models. That is our task. That's what we've been charged with. And we're going to have also an activity on how we characterize, if there are ways to do empirical amplification functions, but the problem is really many of these are applicable for fairly weak motions, not the strong motions that we are expecting. What are our data needs? dynamic soil properties so that we can develop our idealized soil profiles, and data from vertical arrays, which would be very, very helpful. We're trying to see if we can get the data, for example, from the array in Kentucky. That has not happened yet, but that is something that maybe with the data group we can figure out a way to get this type of data. It's sparse, there's not a lot, but these are the issues we are working with right now. Questions or comments?
So back to that list of what we need to do. Yes. This kind of site response model is fine when we have profiles or at least some clear definition of our site. I understood from yesterday maybe 20% of our data has a shear wave velocity. So for 80% of the sites that we need to get site response or site factors for the validation or for evaluations of the paths and so forth, we need site factors. What approach can we be using to do that? Because you're going to get latitude and longitude handed to you.
Okay. So this is now talking about amplification functions or factors at recording stations you're talking about. Yeah. Okay. So this one I was talking sort of in general, regional. So for those ones, we are still trying to figure out what it is we're going to do with the places where we don't have that. We're going to look at using these terrain models, for example, to use that. I mean, you can see outright there's a problem with terrain models. There is no terrain in central U.S., right? There is no topographic relief. So we have that challenge there with those. There is the interesting approach that Paul has based on actual records from using P-Wave. I don't know the detail. I haven't studied the details, even though Paul very kindly explained it to me in detail, but I cannot say it here right now. But it is actually, to me, seems to be a good approach because it is based on data taken from the site. And that is different from sort of a general terrain type of model. We're meeting in a couple of weeks as a geotechnical working group, and this is something we want to talk about. But I know our first shot will be using those terrain models. And the second one would be to probably go for that.
And can Mark Peterson or Chuck, how do you guys feel for using your simplified site classification methods in the East? Have you checked how it works at all? Is it, given the lack of mountains or topography? Can either one of you address that? Yeah. Like mark one out.
Oh boy, I'm not sure what to say.
If you haven't checked, I mean, has there been any checks of like geology versus how that works in the eastern United States?
I did a little study a few years ago for coastal plain and embayment, that part of the East, but we didn't really have any ground truth on what I was doing at that point. It was kind of early. But I think the short answer is we probably haven't really looked at it.
And if I may add, these models give you VS30, and here we are somehow presuming that VS30 is a good indicator of amplification, which we actually don't necessarily think so in certain parts of the eastern United States, whereby, say, you have the Mississippi embayment, maybe the period of the column would be also an important number in this amplification factor. So we have that complication as well.
Ken Campbell again, and I would also invite Dave Bohr to listen to me here because I'm going to reference a paper by his, but I believe that the amplification factors that were used to develop the Atkinson-Bloor 2006 paper used H over V ratios in the east to come up with the amplifications. It's a hard rock amplification factor that's much greater than the original factors that were used prior to that, and I believe it was H over V that was used in the east for doing that. So since these sites are recording sites and will have data, H over V is another approach that could be used. And I think that possibly multiple approaches like that Paul's recommending, as well as H over V and a couple approaches like that, just to get a handle on it, because we know there's going to be a lot of uncertainty, would be appropriate. We're done. It's 0. Okay. I need my glasses.
Before you go, can I, for 5 seconds? So regardless how method you use at the recording sites, regardless of how you estimate the VS or anything else, we are going to get the uncertainty around it, right? So recording such and such, your best estimate of period or VS and so on, plus minus something, right?
Maybe.
There's uncertainty in that.
Okay, we're going to segue to the second part of the geotech presentations this morning, focusing on Kappa, which is a damping parameter. Ken.
Thanks. So Kappa, site attenuation. I just had some comments that we tend to throw out these Greek letters that mean something to a small group of us and mean nothing to everyone else. So the first part of this talk is going to be to introduce what we mean by Kappa, and because that term really is going to be used throughout the project. So I'll look at the use of Kappa in the NGA East project. In particular, this is for reference rock, okay? So this is really a follow-on to what Yusuf was talking about. The velocity, now we're talking about the damping that goes with it. And I'll bring up Kappa for other site conditions. Its definition, its calculation, influence of Kappa on amplification and on the shape of the Fourier amplitude spectrum and the acceleration spectrum, response spectrum, existing estimates of Kappa and CENA, hard rock right now, proposed model for hard rock Kappa, and then discuss some critical issues and data needs. So, use of Kappa in NGA project. It's going to be, as far as I know, and again, we haven't heard from the simulation people, but just based on some of the interaction that I've heard, that Kappa is basically going to be used, site attenuation on hard rock is going to be used to generate the high frequency, typically frequencies less than 1 hertz, so Norm or others can correct me if this is wrong, stochastic ground motion on reference or simulation rock. Now, Yusuf just said we're merging those two, okay, so they're basically one and the same in the simulation studies. The site Kappa operator is used to calculate site amplification factors, typically using the quarter wavelength method. It could be used otherwise, but this is typically, it's used in the stochastic simulation, and stochastic simulation typically uses the quarter wavelength method. And I'm not going to, I'll go into that a little bit, but that's another story. Okay, seismic attenuation. So it can be really thought of as the fractional loss of energy per cycle of oscillation, or in other terms, the exponential decrease in amplitude with time or distance. And it typically, in the past, is thought to have 2 components, a frequency-independent component, which we typically call as anelasticity. So this is the true material damping. And then a frequency-dependent component that's scattering. So typically we think of the material damping as being independent of frequency, but scattering along the path, and even scattering occurs in vertically propagating waves. Scattering then can be frequency component, and there are some competing theories actually that suggest that that's not the case, but this is sort of the traditional way of looking at it. And the Kappa operator is defined by Anderson and Huff, isn't it? I got them mixed up. So it's Anderson and Huff. Amplification is just some amplification A0 times the exponential of minus pi kappa f. Okay, so kappa is the attenuation operator in that, the attenuation parameter in that attenuation operator. And this is the way Anderson and Huff defined it, and it's amazing. We were always used to looking at log-log plots of Fourier spectrum, right, because the amplitudes change so much. They looked at a log linear plot. What happens? You get this at high frequency, this very nice linear fall off, and then you get to noise. The flat part is noise at the bottom, but that linear part is very nice. The slope is well defined, and basically the slope is minus pi kappa f, and you got to divide by log base of natural log of 10 because we're in a log base 10 scale instead of a log base e scale, but anyway, you get the picture there. So that's very nice. You can do that with existing records. In fact, they've done it for lots of different records. However, you can also calculate kappa directly from material properties, and here we get this difference between seismologists and engineers. It's the exact same equation, just two ways of looking at it. So you integrate over the depth, okay, and for seismologists, it's 1 over Q, the quality factor, times beta, the shear wave velocity. And then in shorthand, you can kind of call that H, the depth over which you're calculating kappa, over Q bar, beta bar. Engineers think of it in terms of damping rather than quality factor, and they like to call VS instead of beta. It's the same thing. So you integrate over 2 times the damping over VS. Now, what Anderson and Huff and much of their work and others have shown is that actually you find out kappa is a function of distance. Right? Now we think in kappa 0 is our site kappa, so this is the one that's just based on the crustal profile below the site, but if you look at distance, you can get these kinds of trends. And so they propose this distance equation, and this is where kappa 0 or site kappa was originally defined. So you have a distance component, and the intercept is the site kappa. And that's some plots, I think, at ANZA. These are various sites at ANZA. And then, just to see how it's used, the site amplification using the quarter wavelength method is shown here. So really, you get crustal amplification in the Fourier amplitude spectrum due to changes in shear wave velocity and density, and based on the original definition of Joyner et al. In 1981, and then Dave Bohr has followed on with this. This is the equation. So the amplification is this square root term. Now that's the A0, right, that I showed you earlier. Now A0 has a form. So you're just looking at the beta times rho, the density at the source, divided by the average beta, average shear wave velocity, the average density over a quarter wavelength of the frequency you're looking at. And then you times the kappa operator to give you damping. Here's the impact of kappa 0 or site kappa, or just kappa, on the Fourier amplitude spectrum for 2 different profiles. One is the generic rock profile in the west that Bohr and Joyner had come up with, and then an Eastern North America Niehert BC site profile. Actually, it happens to be the one that Franco developed and is used to develop the factors in the national map to bring it to BC level. But you can see the impact of kappa. Basically, kappa has the same effect in the west as in the east for the same exact value. They're separated just because the amplification is different, but you can see the effects are the same. And also you can see the very strong effects. Even getting the moderate kappa is 0.04 is a typical rock site in California, and 0.01 or less is a typical value in the east. And you can see that huge difference. This is the difference that you see between west and east. It's largely a damping effect, actually. Okay, influence of kappa on ground motion. On the left is let's say a Fourier spectrum in a log-log space in terms of frequency. This is just for 3 different Kappa values. These happen to be the 3 different Kappa values that EPRI proposed in their 1993 model. And then on the right is the effect on the acceleration response spectrum. And just to know, there's another way of calculating Kappa, and this is the one actually that Walt Silva typically does, and that's to fit a model to these things. And if you fit a model to these things, with Kappa 0 being one of the parameters in the model, then you can also determine Kappa 0 along with the other parameters. You would get stress drop and other effects as well. Okay, this version would be model dependent. You're not directly measuring it off the record like Anderson and Huff did. Instead, you're fitting a model to observe ground motions and then interpreting Kappa from that. Now, just to show you some dependence of Kappa on shear wave velocity, these are some models that have been proposed based on some data, various data. A couple of them in a recent paper that Albert Kotke was kind enough to share with me when he was doing some research on something else, and it was a very good paper. So that's the Chandler et al. Paper. They used a couple approaches to come up with a model to Kappa as a function of shear wave velocity, and then a model that Walt Silva has proposed. And so those are just plotted together here. But you can see that there is a strong dependence of Kappa on shear wave velocity. Although, as you can see, you get to the kind of numbers that we're talking about that sort of, it shows up very nicely, that box down there. This is kind of the area we're interested in with reference rock and ENA. So it's way down at the tail. John Anderson at one point actually did a nice little paper in 1996, and he was trying to really put a kibosh on the concept of VS30, because he really knew, come on, from a seismological point of view, VS30 is just, the upward little thinny thing on the Earth, and how that could possibly be related to amplification in the crust. It turns out, actually, that he ended up adopting it and saying, actually, it was quite good. If you have a monotonically increasing velocity with depth, and it can vary, use various different models, it turns out that really all you need to know is the velocity at the top, the velocity at the bottom, right? These are the 2 things you need basically to know for the quarter wavelength method, and the damping in between. And he said the key parameter there is damping. And so it's the Kappa. So we get back to Kappa. He actually interpreted his seismological results in terms of Kappa and actually proposed some numbers for knee-herp site conditions. So turns out we don't have very much data for Kappa in the east. So this is it. This is what I could really come up with. Now, some of these estimates are means based on a range, so actually they represent more than a single value, but we've tried to display it thanks to Albert. Actually, Albert put together a lot of these plots. It turns out to be very useful. So basically the ones from CENA are blue. So you can see they vary between about almost 0 up to about 0.01 for hard rock in the east. Now, just to say, a lot of people have had a problem with such low values in the east. And the idea is, wow, are they really that low? And are there analogs in the west? It turns out there are analogs in the west. And on the right, the green ones are actually very hard rock numbers in the west. On the left of those greens actually are a couple of sites at Anza in Southern California. It's a granitic batholith, very massive. It's very much like eastern rock. It has velocities that are similar to that. Turns out a lot of data has been recorded at Anza. There's earthquakes all the time. Kappas are very small. You can see them. British Columbia on the far right is something Gail Atkinson has done. You're getting a number about 0.01. That rock isn't quite as hard. It's around 1,500 meters per second. But, and then it grades into a very hard rock at fairly shallow depths. So it's not unrealistic to have these numbers. In fact, we can find rock in the west that has similar numbers. here's a little histogram of that data. It turns out actually the mean of that is 0.0062. It's almost identical to the number that EPRI has used and proposed in 1993, and it has been used ever since. It turns out it's not a bad number based on what little data we still have. Well, we certainly have more data than EPRI had in 1993, and we're still confirming that number. Eastern U.S. sites, yeah, not the Western U.S. sites, yeah. That's just the Eastern ENA sites, yeah. Now, the other thing is uncertainty. We got to know kind of the uncertainty in this value. Unfortunately, we don't have enough data to really get uncertainty in the east. But there's a paper by Schneider et al. One of the et al. Is Walt Silva, who's in the back of the room here. They looked at Loma Prieta and came up with some Kappa values for Loma Prieta rock. And they fit several models, came up with some standard deviations. Model 1 and Model 2 are inversions using point source, actually the finite source stochastic simulation model. The sigmas, basically it comes up with a coefficient of variation of about 0.4. So what I'm thinking is, and this is kind of a leap of faith here, but if we can assume that the COV is relatively constant, right, then we can move that COV to our estimate for hard rock, and then I propose this model. So this is just a proposal at this point. Not a proponent. I'm not a proponent at this point. I'm just showing you some statistics, like Yusuf did, proposing a normal distribution, mean of about 0.006. Total standard deviation of about 0.002. That's close to that coefficient of variation of 0.4. Now, the question is, how do we divide that into aleatory and epistemic? At this point, I've just said, make them equal. I think this is an area that we really haven't looked at unless people from the audience can share something. Again, the coefficient of variation is about 0.4, so the 95th confidence interval would be between 0.002 and 0.01 seconds. So, some critical issues and data needs, some critical issues, compatibility with simulation and the geotechnical models. Well, I think that basically we're coming together saying really the simulation and geotechnical rock or reference rock is really going to be the same. So maybe that's not a critical issue at this point unless people think that something different should be done. Its dependence on the velocity. Yusuf also mentioned that Kappa may be dependent on velocity. I've also proposed this as an issue. Correlation with stress drop and other high frequency parameters. If you fit a model to it, like I said that you can do with the Fourier spectrum or even the response spectrum, then there's a trade-off between stress drop and Kappa. And so we've got to make sure that those two things are compatible. You can't just assume a Kappa and assume a stress drop from some other means and assume that those two are going to be compatible. So that's an issue that we have to deal with. Potential regionalization, I don't really think that's an issue, just like it's not for reference velocity. I'm sure if it's not an issue for reference velocity, it's not going to be an issue for Kappa for sure. The appropriate distribution, I've sort of thrown out the idea of a normal, but it could be, log normal or something else. I think these numbers are so small, the range is small enough that the distribution isn't important, but if we were to go to larger numbers for some reason, for other needs, then the distribution may be important. The partitioning between aleatory and epistemic. And then some data needs. Are there other estimates relevant to CENA? As you can see, there's just a handful of values. But some of those represent a range of values, by the way. But still, we're only talking about a handful of values. Are there other areas, other regions where there's data? So far, we haven't really been able to track that stuff down. Should additional estimates be done by the database? We're now going to have this very nice Eastern U.S. database. It's possible that now we could get some additional Kappa estimates from that. Now, should we compile some estimates for other site conditions relevant to CNA? And here I was thinking there may be a difference between reference and geotechnical rock. In other words, we might have this gap in between where we're at something like 2,800 meters per second here, but geotechnical models are starting here, right? And then you have this gap in between. And we might need Kappa, we might need amplification in that gap. So that's still under discussion. We may not have that gap. So we may not have to deal with that. But what I'm thinking is we certainly have different site conditions in the east we have to deal with. The carbonate platforms in the Midwest, right? Granted, we may get to 2,800 meters per second fairly shallow. Yusuf says it could be 100 meters. Shallow is 100 meters in some areas. But we still have that 100 meters to deal with. But, the amplification model may handle that. But there's this issue of, just using a site amplification model. They have a different way of treating damping. Is that consistent with what we know about Kappa? I think we really need to look at Kappa. We need to compare it against the damping that the pure geotechnical models get in their site response analysis, and kind of use that to make sure that we're on the right track. Mississippi embayment, of course, the New Madrid region is a kilometer of very soft sediment. And that will be handled with the site amplification as well. But we also have some very good Kappa estimates in the Mississippi embayment. So whatever we do, the model needs to be consistent with those Kappa estimates. The Atlantic and Gulf coastal plains, of course. And then we have a lot of areas of shallow soil. So we have hard rock with very shallow soil over it. And that's, obviously a residence condition. That's also a site response issue. But anyway, I just wanted to bring some of these up. This is interesting. This Chandler all paper, I'll just throw this out. He's compiled some, well, actually, they had some actual measurements, but they also did some calculations. And they have a model for doing that. And they actually have two models for doing that. And I think most of these are calculations, but I don't know. The paper, unfortunately, doesn't really tell you which ones they calculated and which ones they took from people's measurements. But, if you go down the Korean platform, okay, this is probably a stable region. It's a platform area, much like the Midwest, I believe, and, they're proposing some Kappa estimates that are certainly higher than reference rock. And on the order of maybe 0.02 seconds or something for something as hard as we might expect. South China, the fold system, that may also be an analog area. Haven't really had a chance to track this down. It'd be interesting to contact the authors and find out the basis for that. But go back to this at this point. So some of these issues have already been discussed with when we're talking about reference velocity, the potential regionalization, unless, it doesn't look like that's really going to be an issue. We don't plan on having a difference between simulation and geotechnical or reference rock. There could be this dependence on reference rock velocity, so if we give a range of velocities, we're probably going to have a range of Kappa values that go with that as well. Still, I think we're talking about this 10% difference that Dave Bohr said, because the damping is so low anyway that you change it from 0.006 to 0.005, you don't get much effect on it. Anyway, I would just open it up at this point. Did you prepare anything for this?
Yeah.
Wow, okay. We'll let Norm kick things off here. Once he writes it. Well, one thing is kind of interesting. Does anybody have a problem with using the term Kappa instead of saying site attenuation? we tend to fall into this for those of us that, deal with this. So someone complained about CAD yesterday, right? And a graph. I didn't know what CAD was either. I know what CAV is. I didn't, so I could guess what CAD was. But, so, just using this term Kappa may, in the broader sense, not be an appropriate way to talk about it. But, Jack Boatwright has raised his hand.
For trying to get higher sample rates on the broadband data.
Okay, Jack mentioned that, yes, because Kappa is a very high frequency, particularly on hard rock, a very high frequency parameter that this is a good reason to get higher sampling rates on the broadband data so that we can really sample the higher frequencies.
I don't know if you did a quick calculation, Dave, but my own feeling is for the high frequencies that we're interested in, this is a bigger deal than the shear wave velocity. Is that what we're going to, if we had numbers like 40% COV of Kappa, that's going to be changing frequencies that matter, okay, in a more than 10% way. But I'll let Dave run this while he's okay. I think, so some of the issues that Ken just brought up, so one was the average value seems to be still close to about what we were using before, okay? But then the variability of Kappa, and what do we do with that? And I think that's an important issue. And you talked about whether it's aleatory or an epistemic variable. For our simulations, I think when we go, let's say, go out to finite fault simulations and are really computationally extensive ones, we'll need to use a single Kappa just to keep life easy. All the point source runs, we can deal with suites of Kappa and look at what the impact's going to be. But we're back to what we talked about reference rock, okay? So we said we wanted a suite of shear wave velocities to be captured in our reference rock. That was one of our summaries this morning. Should a range of Kappas also be there? And the question that I bring up here is, if you start to do this, if we bring in too much stuff and treat it effectively as aleatory, that's if we're going to say there's now a range of reference rock condition, that becomes, for all practical purposes, an aleatory variable that we're going to randomize over. Then you start to, one, lose benefits of any measurements at your site where you may be able to say, okay, I can tell my site really does have a Kappa of 0.01 as opposed to 0.006. And when we're going to single station sigmas, that should have been taking out our Kappa at our station, right? And so if we start to do throwing this variability back into the ground motion model, then we're going to be losing a lot of what we're trying to do, is get more, let's say, our single station values. We could have Kappa as a parameter of the model. Okay, so you have a reference rock. It's calculated off of a Kappa of, say, 0.006, but in developing the GMPEs, you could have Kappa, again, as a parameter in your predictive equation, because that's, and Bob is shaking his head no. So come on up here, Bob, and tell us why.
I would say the difficulty with that would be actually being able to get a measurement of Kappa at the reference rock at your site. Below your site, you could get a Kappa at the surface and see. I mean, assuming that they had measurements, and you can get a total site Kappa. But getting Kappa at the bottom before you start amplification, I think, would be a very unlikely case for almost any site that would be analyzed, even a nuclear power plant. Unless Cliff starts asking it, put into the reg guide, standard review plan, that they have to measure Kappa at the hard rock.
go ahead.
Yeah. By the way, using that Loma Prieta, that was really the uncertainty from site to site, right? So actually, it included what we would call inter-site uncertainty. So maybe it's too big, right? It's depending on how it should be used.
So I'll go back to Walt on the sites that you've been working on. Would you also want to just see a range of kappas included in the rock ground motion model? So this is not a parameter to worry about for your site? Sorry, Walt, but yeah.
Walt Silva again, and I think the question was, would we like to have the Kappa variability built into the hard rock GMPE? Is that correct? Absolutely. We want to minimize the number of free parameters for hard rock. Right? As Bob said, we don't want to have to go to a standard review plan that says measure Kappa at your site, or have an expert elicitation for the range of Kappa at your site.
Okay, so range of VS30s, range of Kappas, and all that variability gets thrown into the underlying rock ground motion variability. Are there any other concerns of people who have, especially those of you who've been working on sites, if this is not, or is missing anything that you would want to use on a site-specific calculation? Ralph.
One of the things about this Kappa 0.006 is that if you do a quick calculation, you'll see that basically it would cut off your Fourier spectrum. Basically, you'd be at 1 over E at 53 hertz. And so this means that when we're looking at something when you're looking at the total path. In other words, because this idea, if you're out at 200 kilometers or 1,000 kilometers, which we're supposed to be going to for these finite fault simulations and the like, then what happens is that it's making sure you don't, it's almost like you're not going to double count it because it's so far out in terms of frequency, but it means that the path effect itself, the total path, this K of R term that was also in the Huff and Anderson paper, this is going to play probably a bigger role, in fact, than what's going to happen at a hard rock site. Because we're talking about this is going to affect, parameters out there at 53 hertz and above. Well, most of that might be chewed up before we ever got to 500 kilometers. So worrying about a site effect if you're out there is very little different. I mean, it'd be completely different if you're in close. And also at 53 hertz, now what happens is that if that's really the hard rock site, then this idea that you've got this shallow layer of soil over this rock, it's that shallow layer then that's probably going to dominate what the Q is. In other words, it's not going to be the hard rock Kappa that we're talking about here. It's going to be the Kappa knot that you have in that shallow soil layer. That's going to play the biggest role when you're in close. In other words, because that's going to chew up your energy, because at 53 hertz, you're going to get a lot of wavelengths, and even in the shallow layer, let's say 20 meters, 10 meters or something like this. So it's going to be a different story.
Somewhat contrarian view to that, or opposite view. I may be wrong, but I think the deaggregations often show that magnitudes around 5 at 10 or 15 kilometers are really important. And also a lot of the nukes, they strip off that shallow stuff so that, in fact, some high frequencies are important, and the Kappa could be actually, Kappa 0 could be an important factor.
Just to clarify here, when we're talking about Kappa, we're not talking about Kappa at the surface. This is the kappa of our reference rock, which then gets pushed up into the soil profile later on with all the appropriate damping. It's not kappa naught. This is rock kappa, or kappa naught if you didn't have any soil on top, right, is what we're talking about here. All right? Yeah.
One thing about kappa, it's additive. So basically, you can take the kappa of hard rock of 0.006 and add it to the kappa of the soil, or the damping of the soil. So really, it's cumulative. You can just add it.
Not to get contrarian, but I think Ralph brought up an interesting point, which is that you don't actually have that good an estimate of the Q at very high frequencies. So those estimates are going to trade off with your kappa estimates. I mean, to me, that's a fairly large problem, actually, resolving the Q above the rock path-dependent Q above 20 hertz, and then the kappa on top of that.
So I guess Norm gave up. So let's go back to this issue of data. Anybody aware of data that could help at least get a better grip on the uncertainty, or even the median value, the average value that's going to be used? Is there some Kappa database somewhere hidden? And so, Chuck, then going back to you and singling you out from the database group, you think you would have some information that could be used by the Geotech group on that? You don't have to say yes.
I don't think so. I think
okay.
Given the BS30 that you found, I don't think you've really thought about Kappa per se.
No, okay. So the answer was that they are providing VS30 and some other, you have VS other depths, right, too, right? You mentioned yesterday to a certain extent, but they didn't really consider Kappa, so it's not part of the database. Any other issue you'd like to bring up? Okay.
Can't stay that quiet. The recommendations that we're getting, and I think makes sense, is that we cover a range of kappas in the rocks, so that it's not something people have to try and go out and measure. The variability that we put into that range is then key. And so, Bob or Walt, do you have numbers that you would use on uncertainty in kappa, or let's just put the variability in kappa that we should be incorporating in that rock model? Starting with Bob. Is there an 0.3? 0.3 natural log unit. Okay, that's pretty close to your COB of 0.4, a little small. But what is that based on, Walt? Is there? Yes. Sorry. So Bob has just referenced you as his where he's coming up with the numbers.
Silva again. Yeah, I think Ken pointed out it was basically the range in Kappa values we got from inverting rock sites from the Loma Prieta earthquake. So it was a long time ago. And we did a weighted average, and that came out to, and assumed the log normal distribution, and it came out to a sigma LN of 0.3. And so that's just been propagated for no particularly good reason. It was just a number that we came out with in 93 or so.
This is probably a data need that we need to include in, that we go back and let's look at, even for the eastern U.S. sites, and see if we can't see what the variability of Kappa would be.
Yeah, just a quick comment. It wouldn't surprise me that the variability would increase as Kappa decreased. That seems to also be the case in the uncertainty in VS30 that we developed for NGA West, that as VS30 increased, the sigma, the variability increased.
So this, I think we will send back to our working group on this, and that we've got a center and a range of the VS30s that you're going to say you're going to capture, and we need to do the same thing for the Kappa values. So we'll have to, I think, update what Walt had just talked about of modeling, let's say, some of the hard rock sites in the east, and see what is that distribution of Kappas that fall into the range of shear wave velocities that the reference condition is already supposed to capture. Right? Does that make sense to you, Seth? All right. Anything else? I think we know what we're going to do on this. Paul and Martin, you're remarkably quiet, but is that making sense to you then? Okay. All right. I think we're going to declare this topic done. We have a. Do you need something to say?
Just one plea. I mean, we need data. So if I don't know who's out in cyberspace listening to us here, but and any of you that can go back and talk to your colleagues. But if we can get Kappa estimates for hard rock or CENA type conditions, we really need it. So I would really challenge people to try to develop or propose that. And as like I mentioned, we're collecting data. We can actually, it's a time and budget issue, but if there's time, it would be, and money available, it would be very good to try to do additional Kappa calculations in the east based on the new database, which, by the way, using the new broadband data should be fairly well-defined, I think.
I just want to add a little thing. In your slides, you presented the rock, and sometimes the rock was defined as much lower than CENA and all that. So that I guess it would be nice to have, yes, more data, but really have a clearer idea of what the VS is for each. I assume you have that. We probably just didn't show you all the points, but I'm sure you have that from the publication. The VS rock, that the Kappa associated with that rock VS. I mean, the correlation with VS and Kappa, I guess, which we'll talk about on...
No, not really, right? Because a lot of those Kappa estimates, either if you take the recording and you're calculating, you don't have the velocity. You can calculate Kappa, but you don't know what the velocity is, right?
So then you can just do regional.
Right.
And assume that it's... Okay.
Yeah, so really the two, are sort of...
Okay.
You very rarely have both.
Yeah, that wasn't clear to me. Okay.
So in the note, can you add on your list or someone else's list definition of Kappa?
Yeah. We need it. We'll add it to this in our summary at the end. So we've got to add that they go out and let's try to calculate some additional Kappas, and part of their charge is to quantify the range of Kappas that goes with the range of the VS30 that will be declared what our reference rock site encompasses. Clear, right, Yusuf? No problem? Okay. 2 Yusufs right there. All right, let's take our break. We're going to start early, or are we going to start... let's come back in 20 minutes. How about that? 5 after 11.
No, I'm fine. Just what I... It's been with us. I'm going to blame Lauren.
understanding of almost understanding because others random vibration. And if you just purely random vibration in low frequency, it can be positive, it can be negative. But you have somehow built your model, low frequency, it can be positive. So that's the basic that's why research is purely random phase. So yes, positive is a positive negative. So geologic, they don't have dynamic. Which say low frequency representation was the static part of the physics of the the people giving us from experts so you did something different. Everyone like
Yeah. And clicking is here again.
Yeah, you can go ahead with this one or with the mouse, whatever you prefer.
And page back, page up, right? Arrow? Okay, forward back.
It doesn't appear with the
Okay.
I'm not actually going to use that.
Yeah. Yeah, there's some things I want to point out, like, and I can find the mouse. Yeah, this one. I'll move closer to that. Thank you very much.
Okay, everyone, it's time to come back. It's now 11:10. We're going to start again as soon as we get Norm back here. Grab your coffee, sit down. Yeah. So do you want to do those back to back, or you want to have the discussions after each?
I think having a discussion after each would be better.
It's usually better. That's what I prefer. Because then you focus on it. Okay. Good.
And based on an earlier one, this is parse differently. So I have single double. First part is going to talk about validations from single and double.
Oh, okay.
If you wish, I can defer this.
No.
Because now it's moved down here. It used to be up here, now it's moved down.
Yeah, I know.
It's up to you. I could do either one. It's whatever you think is better for the flow. I believe this would have been better. If I had more time, I would have changed it. But I'm not good at PowerPoint, so.
That's fine. So if you want to do that, will you have, because you won't have time to update your slides, so maybe you can, whatever seems more natural for you.
Okay, I'll just say we're going to do this in the second part.
Perfect.
Based on a revised agenda. That's fine. Okay,
everyone. So we're going to start the second half of the morning session. We can please have your attention. Order. I need a hammer. I don't want to scream, right? Hey, let's go. We start. Okay, party time. So Bob Dara is going to do the next two talks. And in the first one, he's going to focus on the different models that are considered for point source simulations. And then we'll have a discussion, and then we'll focus on issues with point source models, and we'll go over that. Okay, so thank you. Bob?
Welcome. Good morning. This morning is the first talk on potential models to be used in Central Eastern North America. And I'm going to be reporting on some work that Walt Silva and I have done at Pacific Engineering Analysis. Okay, the first part we're going to look at is validations. I put up Central Eastern North America just to get your attention. we really have done very few validations on Central, Eastern, and North America. So the focus of my talk will be on Western North America. And in particular, we're going to look at stress parameter dependencies in Western North America with the implication or hope that they will be able to be transferred to Central and Eastern North America, or at least used for guidance for stress parameter or stress drop estimates in the East and Central U.S. We're going to look at three stress parameter dependence on moment magnitude and on slip depth, which we define in a couple different ways, either moment release or TOR, which is top of rupture. For moment release, we define shallow slip as 20% or greater of the slip being in the top 5 kilometers of the rupture. And deep slip is then the opposite. Less than 20% of the slip is in the top 5 kilometers of the rupture. In Western North America, we have quite a few deep and slip events. In Eastern North America, the top of rupture or the depths of the events tend to be deeper. So in Eastern North America, the trends will be looking at what's happening between shallow slip and deep slip in Western North America, particularly California, and seeing if that has any implications for the East. And then we're going to look at some trends in mechanism between the classic three mechanisms: strike slip, normal, and reverse. I may get to single versus double couple in the first part of the talk. That's why this is here, but that may also be deferred to the portion of the talk after lunch. Oh, no problem. Should I start over a little bit? No? Okay. Okay, we're going to look at Western North America validation studies, and Walt and I have done two types of validation studies. One is the point source using a single corner model, and the other is a finite source model. And these are both stochastic, band-limited white noise ground motion models for the West. So here's a table of our favorite earthquakes that we've used. There's actually now two parts of the table because due to some recent earthquakes that we've added to the NGA West database, particularly Parkfield, San Simeon, the BAM earthquake in Iran, and Totori, Nagata. The database is increasing. But the classic part of the database that we've done most of our analysis is back on the first page. And we have, going from your left to right, earthquake name, its year, its moment magnitude, mechanism. And mechanism is defined on the second page, but zeros are strike slips, and ones are normals, twos are reverse, and 3 or 4 are some combination of reverse and oblique or normal and oblique. Then we define slip depth as either shallow or deep for the earthquakes, top of rupture, the number of stations in the inversion or the validation, the distance, and the distance is a distance from the station to the ruptured fault plane, and then we compute just a static stress drop, which comes from the circular model for computing stress drop, and a stress parameter that's used in the validation, which gives the best average fit to, say, San Fernando for the 39 stations, ranging in distance from about 2 kilometers out to 219 kilometers. Both slip depth and top of rupture are defined from a finite rupture model that for most of these sites down to 26 was used in the NGA West model and was vetted through a group of seismologists to come up with what they thought the best rupture model was that showed where the concentrations of slip were. For the final 5 models, that's in a NGA follow-up project, and those slip models are the ones that we prefer at Pacific Engineering Analysis, but I believe USEP is going to have a group get together to see if we need to adjust those models in any way. So this is basically the data set we're looking at, and then we're going to just show the results of some of the analysis. So this is looking at 16 point source. So this is data from earlier on, and we're going to look at, this is nonlinear soil response at 503 sites. The top slide shows the modeling bias. And if you have a perfect model, you'd want to have it at zero bias. And basically, we're very close to zero bias out to about 1 hertz. And then from 1 hertz to shorter frequencies or longer periods, the point source model overpredicts the data. And this is the reasons why Gail Atkinson went to a double corner model, was looking at these types of results from the point source model. Below that, we show model variability, which is roughly about 0.5 and increases as frequency decreases or period increases. And this is for 16 earthquakes. So that's from the point source model. The next thing to do is see, well, how does the finite source model work? And these are the results from the finite source model. And you'll notice that the finite source model has improved the model bias. It basically runs around zero now all the way out to roughly 0.3 hertz or roughly 3 seconds. And this is done on the earlier data set, which is mainly dominated by records collected from SMA instruments. And that's why so far these results only go to basically 3 seconds. With the new data, we hope to be able to extend it out to longer periods. So the low frequency cutoff is based on bandwidth from the recorded data. Okay. Oops. So just to show you again, this is from the point source model and from the finite model. Okay, so that kind of covers our modeling results. And then we have some observations on stress parameter based on this set of data. And one, it's in Western North America, the stress parameter will decrease as magnitude increases. It varies with fault mechanism. Records from normal faulting have smaller stress parameters than strike slip, even though they're just slightly smaller than strike slip. But reverse fault mechanisms generally have quite a bit higher stress parameters than strike slip. The third observation is that it increases as slip depth decreases. So shallow slip is defined as 20% of the moment released again in the top 5 kilometers. We're going to show you some slides going over this. Okay. Oh, excuse me. And then we hope that in the West, and by extrapolation, Central Eastern North America, that the variability we see in stress parameter can be reduced by an explicit accommodation of the epistemic component, which we can see in both slip depth and rupture mechanism, and that can reduce your aleatory component. Okay. So you can see this slide. We have stress parameter, which is estimated from our modeling results, versus moment magnitude. And there are 2 types of slip shown. One is stress parameter from deep slip earthquakes, of which there are 6 in our database, and they range from Coyote Lake, which is a strike slip earthquake in Northern California, to Whittier Narrows, which is a deeper earthquake in Southern California. And this slide is suggestive that as you increase in magnitude, stress parameter decreases. There's also a couple other variables involved in this. Generally, for the large magnitude earthquakes, you'll notice we have no deep slip, large magnitude, greater than magnitude 7 earthquakes in our data set. Large magnitude earthquakes tend also to have surface rupture, much more concentrated slip near the surface, and hence lower stress parameter. Okay. This is stress parameter versus top of rupture, and this shows one of the clearer trends. As top of rupture increases, it goes from 0 to 16 kilometers, and the X around 3 kilometers is from Coyote Lake. The cross at 15 kilometers is from Whittier Narrows. And you see quite a bit of scatter in the shallow earthquakes, ranging that have top of rupture from basically 0 to 2 kilometers. The stress parameter ranges from below 10 to almost up to 50, 60 bars. And if you look at the stress parameter from 6 observations from the deep, it's tightly clustered around about 58 bars. This we summarize in this table. And these are preliminary estimates done by one of our colleagues at Kappa in Korea. So now we're looking at a set of 24 earthquakes, 18 shallow and 6 deep, and the stress parameters are summarized, and so is the standard deviation in log space. But basically, there's a huge and significant difference between the stress parameter for deep earthquakes, close to 52 bars, and for shallow earthquakes, closer to 24 or 25 bars in Northern California, in California in general. And also the sigma decreases quite a bit. There's quite a bit of scatter in the shallow earthquakes that isn't observed in the deep earthquakes. This is looking at it among the three variables, the third way to look at it. This is for just a set of 24 earthquakes. This is looking at top of rupture in the y-axis versus magnitude. And we now show deep slip as triangles and shallow slip as circles, again showing similar trend that as you increase in magnitude, you see the increase as magnitude increases, the top of rupture becomes closer and closer to the surface in Western North America. This is from a more limited data set. We also have a broader data set showing basically the same trends. Once you get about magnitude 7, most tops of rupture, at least for Western North America earthquakes, are very close to the surface. So now we'll go back to some validation studies. To do this, we looked at the 4 NGA West ground motion prediction equations, 3 moment magnitudes, 5.5, 6.5, and 7.5, and about 7 distances, ranging from JB distances of 1 out to 200 kilometers. We're going to focus on some results for soft rock with a VS30 of 550 meters per second, but also in the version we had a soil site with a VS30 of 270 meters per second. Now this is a very busy table, so I'm going to show it to you again at the end. The top column has 3 magnitudes, 5.5, 6.5, 7.5, and it shows the stress parameter for strike slip, normal, and reverse earthquakes. And there's a couple trends you can see immediately. For all 3 fault types, as magnitude increases, stress parameter decreases. And you can see that in strike slip, it decreases from 66 bars down to 23 bars. For reverse, 56 bars down to 29 bars. You can also see the relationship between the 3 fault types. Normal fault types have the smallest stress parameter for all magnitude levels, and also the smallest median stress parameter. Strike slip is only about 10% larger. However, reverse is approximately 50% larger, 25 to 30% larger than, say, normal or strike slip. And you see that for all 3 of the magnitude levels. The next middle section looks at top of rupture, and we have 3 tops of rupture. Our default top of rupture we use in the inversion for magnitude 5 is 6 kilometers, and for magnitude 6.5 is 2 kilometers, and for 7.5 is 0.7. We came up with those numbers by looking through the NGA database, and where we had rupture models, which is mainly the 6.5s and 7.5s, we averaged the top of rupture to come up with those numbers. For the 5.5, we looked at kind of the average hypercentral depth for the earthquakes, mainly in California, to come up with a depth of 6 kilometers. For shallow slip models, we just set everything equal to 0 kilometers for rupture to surface, and for deep slip, we held it at 6.8 kilometers. So the second group shows, and this is only for the rock site only, even though the inversion included both rock and soil, you have strike slip, normal, and reverse. And again, you see the same patterns you saw up above, in that as you increase in magnitude for basically all fault types and all slip depths, that the stress parameter decreases. And then if you look across the table from shallow strike slip to shallow normal to shallow reverse, you'll see that the normal is just a little less than the strike slip, but that the reverse is quite a bit greater. And we see that trend looking at shallow, deep, and our default depths. Now, how did we get to this table? So this is the modeling that we do. So this is for Abraham and Silva. This is the soft rock. VS is 550 meters per second. We have magnitude going down the page, and we show depths, we show 1 kilometer, 5 kilometers, and 10 kilometers. Magnitude goes across the page. Magnitude 5.5, 6.5, and 7.5. In the next slide, we have 20, 50, and 100 kilometers. And in the final slide, 200 kilometers. So we're trying to encompass the range of the GMPEs in the west, and also a range of magnitudes from 5.5 to 7.5. There are 3 curves on each plot. The 2 curves to pay most attention to are the solid curve, which is the data, and this is the Fourier amplitude data. So we compute a response spectra. The response spectra comes out naturally from the ground motion prediction equation. To that, we do a match to it to get a Fourier amplitude spectra. And the smooth Fourier amplitude spectra is what you see as the solid line. The dashed line is the output from our model. And basically, it's a band-limited white noise ground motion model where the magnitude is fixed, and we basically are fitting kappa at high frequencies and attenuation, which we use in the model of Q naught F to the eta, and also the stress parameters. So those are basically the 3 parameters we're fitting. And you can see where this shows a fairly good fit on both magnitude and distance. As for very close in, the farthest one to your right, the top is a magnitude 7.5 at a distance of 1 kilometer. The Abraham and Silva model, we did all 4 models, shows the worst fit in this particular analysis. The Bohr and Joyner one, Bohr and Atkinson shows the best. So we want to show you a range of what the NGA models show. And then as we increase in distance, you'll see that particularly still 20 kilometers, the fit is quite nice. As you get a little further out, especially at 200 kilometers M75, the shape of the Fourier spectra and the shape of the model are not that close for this model. Then we go to Bohr and Atkinson. Again, the same set of slides, magnitude 5.5 from 1 to 200 kilometers, 6.5 from 1 to 200 kilometers, and 7.5 from 1 to 200 kilometers. You notice especially the larger magnitudes, the fit in the Bohr and Atkinson model is very good. And we did this also for the for Bob Young's model and for Ken's model, but we're not going to show those results. But they are included. They are included in this average. So this average is over the 4 GMPEs. Okay. And there are trends between the different GMPEs that we're not showing here that we've looked at also. All right. So I probably want to go over this again because it's a very busy slide. It shows basically some of the results we think might be transferable to Eastern North America. One that's definitely not new is that as magnitude increases, stress parameter decreases. And we see that for all 3 fault types and over all the NGA ground motion prediction equation models. We also see that as the top of rupture is deeper, the stress parameter increases. And we see that again for both strike slip, normal, and reverse faults. And the last thing we see that's also incorporated in the GMPEs is that almost all the GMPEs have some sort of fault type, and the motions from reverse faults are larger than from either normal or strike slip, and that's reflected in our model by a larger stress parameter. Okay, so I still have 11 minutes left, so I can either go on to single versus double couple, or we can start discussing this right now. Norm, what do you want to do?
Stop the presentation right now. Let's talk about
okay.
That's fine. So, sorry.
Well, that's okay. Hey, no.
We're trying to figure out, what's good. All right. Let's go back to some of the earlier validation part. And
so point source.
Point source, yeah. We're going to start with the point source model. And so we can start with sort of this. This is the way that we've been doing validations in the past, right? So many of you know over the last 20 years probably, we've been looking at model bias. Yesterday we talked a little bit about other parameters we may want to use for validating models, but for the point source stochastic model, fundamentally you're not producing a duration, you use a duration, so we're not going to have those other kinds of parameters. But we've got here an issue of bias that I assume we're going to talk about later with the double corner model. Meaning we've got
an
overprediction to live with.
Periods.
Right. When we start to go to, did you have anything in terms of by earthquake? I'm trying to think. 'Cause the one issue that we face on these values is how well does the point source model actually work being close to a big earthquake, right? Because conceptually you think point source and big earthquakes don't fit together, yet I think what you were showing earlier, or even later in the comparisons to the NGA model, they worked quite well at the longer periods. And there you've got big earthquakes, right?
This is a big earthquake, enclosed.
So I think we need to talk about how you make the point source model work for a big earthquake. So this is comes back to equivalent point source distance, right? So do you want to? Did you make it clear how you guys are doing that, or? So
there's some. I'll go through these. So there's some in here. So the equivalent point source distance. Sorry. So we use, we basically just use JB distance. But for the point source, we also put it at a depth. So for a magnitude 5.5, so for our 5.5, we'll have it 6 kilometers deep. And then we run it at distances of 1, 2, 5, 10, 20, up to 200. Now, you're talking about the simulations or about the data? When we're modeling real data?
Modeling the data. So we're just talking about just the validation part. Trying to fit data, let's say Denali.
Right. This is pump station 10.
What is your point source distance?
Since Denali ruptured the surface, we use JB, 2.5 kilometers.
So just that I'm clear, you're using a distance metric where the fictitious depth is the top of rupture. Is that correct? If I'm thinking of it that way as a joinder bore distance plus a depth term?
For this one, we would use that, but this one, the fictitious depth is 0.
Correct. Yeah. Okay, and then another one, wherever it is, you're putting it at the top of the rupture.
Right.
Because I think that's going to be...
So we would go over and then down to where the rupture is. Right.
Yeah, so I think we all just need to be clear what's happening here in terms of how we're using those distance metrics.
We would like to use a slant depth as opposed to JB. We use like a slant depth. Depth to the ruptured plane. So you look back at this. Yeah. So you look back in here in San Fernando, Pacoima is right over the ruptured plane, so the distance would be 0. But we're using 2.1 because that's the distance from Pacoima down to the San Fernando fault plane. So that's the distance we use.
The definition of the closest.
Yeah.
Yeah.
So we use it in these guys, we use the distance basically to the fault line.
So, in really simple terms, the equivalent point source distance that goes into the stochastic model is, in one case, a rupture distance. Is that correct? Or as opposed to a joiner bore distance with a depth to top. And those are two different things.
Right.
So
it'll tend. Some of the confusion is if we're going forward modeling or backward modeling. How do we do it?
We need to be consistent, right? However you go backward, we need to use the same methodology going forward. And so I've been beating up on you a little bit just so it's clear what the definition is, so everyone knows when we're saying point source model, we're not putting things at a hypocenter, we're putting them at some closest point. What are you trying to say? I'm sorry. Dave.
I'm not sure if this is relevant or not, but I published a paper not long ago where I was comparing the finite source XM calculations to the point source, and I found that in close, if you define a new effective distance, which actually turns out to be like the RMS distance, it's in the NGA flat file, you've got a better comparison. And the same effect actually is in the Atkinson and Silva 2000 paper, where there's an H as a function of M.
Right.
And so, and it's also similar to what Frank Scherbaum has found when he was trying to do point source modeling, that if you use hypocentral distance, it works better. So something like Denali, you would actually use a greater distance instead of just the closest distance to the fault. It seemed to have a better comparison using point source simulations when you had in effect, having a pseudo depth that was a function of magnitude. So if you're at a given fault distance, as the fault increases, you have to actually increase the distance in your simulations for the point source because more distant stuff is contributing. Yeah.
Have you guys looked at that in your inversion? I don't know, Walt, if when you were doing the inversion using either a constant fictitious depth or, is it always been the depth to top of rupture that is used? As Dave is saying, for magnitude 8, maybe you add a fictitious depth of 15 kilometers or something like that just pushes it downstripe. The depth of the center of the largest disparity? Okay.
And what we were going to do is test it, also try and magnitude what we use
Okay, so what he's saying is when they are modeling the ground motion models, the NGA models, you use simply a magnitude dependent depth, which is somewhat what like Dave was just talking about. So, Walt, I'm going to have to force you to come up. Sorry about that.
Well, Walt's coming up. These are the fictitious depths we use. So we have default, where at 5.5 it's 6, shallow it's 0, and then deep it's at 6.8. And then Walt was going to refer to, I believe, a plot like this.
Yeah, thanks, Bob. Is this one? Yeah, I think there's. It doesn't matter. I can't get the cursor to work on here. Oh, okay, great. So this is magnitude 6.5 at a JB distance of 1 kilometer, 7.5 at a JB distance of 1 kilometer. And whatever distance metric we're using, or depth, it seems to work pretty well, going out to 5 kilometers, JB distance of 10 kilometers. So this was just to demonstrate that simple assumption of a depth that's magnitude dependent and a JB distance does reasonably well for a point source model. And for the validations that Bob was showing, we actually used the depth to the center of the largest disparity.
My first concern is to make sure that we have consistent approaches used in the validation as what we're going to use in the forward modeling. And so if we're using depth to the disparity, we're then going to have to randomize that. And if we just use something like a depth-dependent or magnitude-dependent depth and did the validations, we'd still, I assume, get a reasonable model.
You're correct, sir. And the variability will then reflect. It should be a little bit higher in terms of variability. It just depends on the distribution of distances in the validation.
So in trying to use these results, if I go to Bob or Dave, Paul, and Martin as well back there, my preference would be to have something simple here so that we don't have to deal with randomizing that in the future and just live with the increased standard deviation from the validation. Do you all agree with that approach? Yes, they're nodding their heads. Okay, so I think in moving forward on the validations, we're going to have to make sure we get back and have everything done sort of one pass through in one consistent way, and then we get out the biases and modeling variability out of that. You had some comments about epistemic and aleatory and a partitioning of those two. Right. And could you go through that again?
Sure. This is the key slide that shows basically stress parameters computed from 24 NGA earthquakes. And we're looking at stress parameter, which is estimated from our inversions, versus top of rupture. And there are basically 18 earthquakes with shallow, the crosses, and the X's, and the crosses are the deep earthquakes. And you can see just off this figure that the deep earthquakes, these 6, cluster very tightly around about 50, 55 bars. The shallow earthquakes, which are down here, have basically, the max is basically the same as these guys, but they go down to very much lower stress parameters. So there's much more variability in the shallow earthquakes than there is in the deep earthquakes. And the deeper earthquakes tend to have, all do have basically higher stress parameters than nearly all the shallow earthquakes. And that was summarized in the following table. We're here, we're looking at, there are 24 earthquakes, 18 are shallow, and 6 are deep. The median stress parameter for all 24 is basically almost 30 bars. For shallow, it drops down to about 24 bars, and for deep, it's at 52 bars. And the sigma, the variability, basically in shallow and all is quite similar. But the variability, you can see from this figure, for the deep, let's want to go back, is quite a bit less. And then, sample is also a lot smaller, right? And it's not clear we're going to get, there's sample size issues. There's also large magnitudes tend to rupture the surface, and smaller magnitudes do not tend to rupture the surface. The largest magnitude in the deep is either Northridge or Loma Prieta. In that, the 6 earthquakes in that are Coyote Lake, Whittier, Northridge, Loma Prieta, Little Skull Mountain, and one other one that I've forgotten. So, yes, there's quite a bit, and that's shown. It's a much more complicated slide. Looking at top of rupture versus magnitude, you can try and sort out trends in top of rupture versus magnitude in that one. But this may be indicative that for in the east, where ruptures tend to be deeper, one, the stress parameter is higher and perhaps has less variability. And that led to, where'd it go? The statement that Norm was referring to. There it is. So stress parameter variability may be able to be reduced because we see this relationship with slip depth, and then what's also being done, which is redundant, with rupture mechanism. That's already been well known that reverse faults have higher ground motions and hence in our model higher stress parameters than either normal faults or strike slip. Did that clear it up? No? No. Okay.
Well, cleared up a bit because I wasn't clear on that transition there. But it seems to me there's data needs or simulation needs, because those 6 points, are, I mean, you have 6 points on the left as well. I see a trend, but I think we really need to look at that further, especially if we hope to separate the part that's epistemic and aleatory there. And, so data needs slide.
So then we have to
simulations, more earthquakes.
And in the east, there are very few. I mean, at this magnitude range is probably two points total. So the whole issue is, in trends you see in west, be applicable to the east.
Yes, so that's the question, then how we're going to assess the variability for the east. And again, is it again a case that because we have less data, we see less variability? And should we then apply what we see in the west to the east, or at least to some kind of transition in between? I mean, that's a legitimate question, right? Ralph Archuleta coming for a comment.
Well, there's a paper out by Bettina Allman and Peter Scheer published in JGR 2009, where they looked at 874 earthquakes worldwide. And in fact, they developed it basically using a similar method to this one, basically looking at a point source, to represent corner frequencies and Brun-type spectrum. And what they found, they looked at magnitudes between 5.5 and magnitude 8. So they were looking at, and they looked at a large number of stations when they were doing the average. They found two things. One of them is that they found that the average stress drop, the median stress drop that they were getting, which I presume is something like the stress parameter, was about 36 bars. But they also found that there was no depth dependence that they could see. Now, they were looking at all different types of earthquakes. But if you look at, even as they break across the different, whether or not they're basically whether or not they're continental, whether or not they're subduction zone, whether, they were looking at all different types. But there was no systematic variation, and the range of stress drops that they had was very, very broad. And but they ended up with basically what looks like a log normal distribution of stress drops, and it's a very wide range, but they saw nothing systematic with depth. And I don't know whether or not it's relevant, but they looked at worldwide earthquakes, and and so there's a very large data set out there, 874 earthquakes, and even if you break it down, it's more than in some of these areas. They have certainly as many earthquakes as we're talking about here, which is about 24. They were looking, they're looking at, when they're measuring the depth, they're taking hypocentral depth. Yeah, they're just taking this as a point. Basically, they're modeling them as point sources. But they did see, when you look at the overall trend of the, let's say, the scatter on the amplitudes, even though it doesn't look that way, but basically, certainly as they got to larger amplitudes, it looked like the scatter was going down. Now, that may have been because they had fewer magnitude 7.5s and that, but at least looking at the data, it sort of indicated that maybe that there was less scatter at the higher values. But the range of stress drops was all over the board. In other words, everything between 1 bar and in some cases 1,000, but certainly at the magnitude 5.5s. Pardon? The reference is Allman, Allmann, and Shearer, Shearer. It's in JGR 2009. They also have another paper by Peter Shearer, Herman Prieto, and Egil Hawkson in looking at earthquakes 1.6 to 3.1 in Southern California. And interestingly enough, they see basically the same distribution as stress drops. In other words, same log normal distribution with almost the same median. That one also is published in JGR, but that is 2006.
So I think we ought to look at those papers, but when I was talking about data, of course, I was thinking that maybe when we're going to select which priority of data we can look at, what we can gather from what Gabe has collected. Oh, he just looked, there might be things that we could do there from those larger earthquakes in other SCRs, maybe. Just a suggestion. I don't know if we want to go to that much depth or if we just want to use published values or if they're applicable even. But that's just something to consider, I think. Paul? And then Ken, Paul's footage?
Yes, I have three comments. First, an interesting earthquake that might be useful is the 2007 Shuetsu earthquake. I don't know if it's too late to add data to this effort, but it was a big thrust earthquake, deeply buried with at least one station on the hanging wall, well recorded. 2007 Shuetsu Oki, Japan. The second question is, Bob, could you clarify, you've talked about two parameters, top of rupture and shallow slip, and you define shallow slip as more than 20% of the moment in the top 5 kilometers.
Correct.
Are those two different parameters?
Yeah.
And, okay, so they're actually two parameters you've been using.
Right.
Okay. And my third comment is just from trying to understand what you've done. And Norm said this probably too. A lot of your parameters in the inversion are basically aleatory variables. In other words, things that are unpredictable in advance, like depth of the largest disparity.
Right.
And it would be a little easier to understand your results if you could run the inversions with all these parameters cleared out or somehow fixed so that you can see the actual predictive power of the method.
Okay. So just Paul, on your first point, Shuetsu has been processed, and I believe the data is available at Peer. So all that data set is available. The second question is, how do we get slip depth versus top of rupture? All these earthquakes have a finite rupture model, which through the first 26 are in the Peer NGA database. So from the finite rupture model, we could see, did it rupture to the surface? What's the top, where in the modulo, where did the modeler place his top slip? So say for San Fernando, it's placed at the surface. In Tabas, the slip in the model that was used in NGA stopped at 1 kilometer. So then to get the difference between top of rupture and slip depth is we look at the slip distribution in the preferred model, and we determine whether or not 20% of the slip is in the top 5 kilometers. If it is, then it's shallow slip. If it's not, then it's deep slip. So say, for example, both San Fernando and Tabas are shallow, and Coyote is one of the deep slip models. And Paul, you had 3 points. I think I only addressed 2. Oh, the other was what to do in the future. Yeah. Right. Well, in the forward modeling, in this example, the parameters magnitude is fixed, distance is fixed, and we run 3 different types of depths. The only parameters that we are inverting for are stress parameter and Kappa, and usually we fix the Q model. So we're down to 2 parameters in the inversion. So I don't know if we can go fewer parameters. In this type of forward modeling, we've already really limited the number of parameters that we that vary between, well, that we invert for. We fix as much stuff as we can.
Let me interrupt you for a second, Bob. So to try to keep us clear on terminology, we're going to use the word forward modeling when we're predicting ground motions for future earthquakes for use in our simulation. So when we're going to turn the crank on and generate lots of them. What you're showing here, we would still call an inversion or fitting. Instead of the individual earthquakes, you're fitting a GMPE, right? Okay, so this is, let's not use the word forward modeling here. We'll still call this a validation, but it's a validation against how well you can mimic the behavior of an empirical GMPE, okay? I think what Paul is getting at, and for simplicity, it helps us that, as we talked about before, any parameter that you use that's effectively not a parameter in the hazard calculation, right, which is going to simply be, we have a rupture dimension, we can randomize that thing, and we're going to move it around in space. But any other dynamic parameter on the slip or anything like that, we don't bring along in the hazard run. So if it's brought along in the validation, we have to then randomize that. We got a penalty to include its variability, and we must, require your modelers to then say, you got to give us a PDF of any of those parameters so that we know what to do with them in the forward sense. The alternative is to simply live with a little worse prediction, but have a fixed rule, like a fixed rule on depth, okay? And top of rupture for us is a lot easier because that's a parameter in the hazard calculation. So if we went to one of your pictures back there, depth to top of rupture is no problem, right? That's all available inside the hazard code. And if we use that as opposed to shallow versus deep slip, life is easier for us, right? And I think it's not, in this particular case, not buying you a whole lot more to have that separation, even though this could be more physical, if you want to think of it, or more greater understanding, but we got to simplify things. Is that what you were getting at, Paul? Yeah, okay. And Bob's nodding his head as well. So I think as much as we can limit variables, especially on the point source stochastic model, I think is one that it makes sense to keep it really simple in its application and not have to then add on a bunch of randomizing variables in the future. For all the finite source models, we're going to have to pay that penalty. There's no choice but to crank out multiple slip models and hypocenter locations and those types of things. Okay? So what we need, if we're going to get back to what we're trying to get out here, I think we've got to get back to set the validation exercise that we need to happen for this project, that we try to set as many parameters as simple as possible. Let's use a fictitious depth that's only dependent on magnitude, so it'll be a rule. And we can use top of slip is fine. This, in my view, will come out in terms of how we're going to deal with the model of the stress drop, right? So when we go in our forward model, we can say stress drop varies as a function of top to rupture, then we know what to do, okay, because we can basically build that into the GMPE. Whereas, or we could say, the magnitude dependence of the stress drop gets built into how we take all of these suites of simulations and say, all right, when it's a magnitude 7, it's 50 bars median, when it's a magnitude 5, it's 80 bars, or whatever it's going to be, such that we can get the GMPEs to come out that way. And I think there we're fine. But here, I think the first step is to have you go back and re-look at the validations, perhaps as adding the event that Paul was talking about, or if there's any other key ones I guess mainly adding buried ruptures, right, are the ones that we're mainly interested in. But, yeah, you said.
They're going to go to 30 plus earthquakes, right? Yeah. Now you have to, okay.
Yeah. Well, there's 24, but we eliminate aftershocks. So this goes up through Nagata. We haven't added Chuetsu, Iwate, or Wenchuan, or the Sierra Alma. There's an additional 5 earthquakes that haven't been, we haven't had time to do that yet. 2 in Japan, 1 in Mexico, and 1 in China. That was big 4.
Ken.
I just want to make a comment regarding this idea that uncertainty in stress parameter or stress drop may decrease with depth, even though the few data points here seems to imply that. There's a very recent paper in the BSSA by Dave Bohr, myself, and Gail Atkinson, where we take 4 different possible path models for the East. We take the 8 best recorded earthquakes in the East and invert that using the point source stochastic simulation model to get the stress parameter. And there's a couple of things that come out of that. I would suggest that everyone look at this paper. The number one is that it's highly dependent on the path, because most of the data you're using to do it is at large distances where the path effects have a huge impact. So if you use, depending on whether you use like 1/r attenuation or you use a very steep attenuation with a large MOHO bounce type of path effects, the average stress drop, or the median stress drop from those 4 models can vary anywhere from something like 30 or 40 to several hundred bars. So that's one interesting thing. The other interesting thing is then for any given path, the stress drop for those 8 earthquakes varies drastically. So the implication here is there's lots of uncertainty. And again, like every other parameter we've been looking at, we only have a handful of earthquakes here that really are that we can use to do this. But so again, I would encourage as much data and interpretation of that data as possible to try to get a better handle on that. But the uncertainty is huge, so I think we have to be very careful about trying to use data from the West, for example, to propose something like that.
Following up on that, so here we can, from the validations you've shown, we can say, here's how well the point source model works, right? Here's its model bias, its variability. Here's let's say the sigma on the stress drop, and do we see magnitude dependence or not in Western data, but what are we going to do for the Eastern application? So we need the median, and if it's magnitude dependent or not, or depth dependent stress drops for the Eastern United States. So I know as part of the validation exercise that we're doing for all of the models, you're going to run the point source model for the few earthquakes we've got. We only have, how many? We're doing like 3, right? Eastern events or 2 Eastern events. Okay. The data that we had before, though, the data sets that were used in the EPRI model, where we had 20 or so earthquakes. I don't remember if you were doing those, Bob, or they were Gale stress drops, but that we had used to set the median stress drop that was in the EPRI model or the Toro et al. Paper. So, Gabe, do you remember where those came from? All of those earthquakes that we had that were, I think they were Gale stress drops. And is there a need to go back to those data and re-estimate those stress drops? Or what? Can you come up here? Sorry. Everyone's getting their exercise. Because that's fundamentally what we have to have, right? We need to come up with a distribution for the Eastern event.
Yeah, I would say we should re-estimate those for several reasons. One, probably path parameters may have changed a little bit as people have a better understanding of ground motion. Also, we will have more events, so I think that exercise should be repeated. And one thing that comes to mind as an aside, and again, we saw this very little scatter for the deep slip event, and Saguenay immediately comes to mind to me. That was a deep, or maybe very deep. Maybe it's not a matter of shallow versus deep, but the very deep ones may be another story. And of course, that gets, as John Adams has mentioned many times, that gets complicated by path and directivity and a lot of other things. So yeah, we should be very careful to ever assume low uncertainty, because nature tends to fool us there. Say a lot more than you expected me to say. Sorry.
No, that's okay. So one of the tasks I think we need to put down, Christine, is let's be sure that we're running back to essentially the data sets we were talking about yesterday, all the events that make sense, that we basically pull out stochastic stress drops that fit with the same way we've been just talking about the model. If it's a join your bore distance with a fictitious depth, that's the way a single scaling for the depth term, or whether it's the actual top of rupture, which is easily to use as well in the hazard. Dave.
Well, just to reiterate what Ken said, if you're going to do that, you're going to have to do it with different geometrical spreading and Q functions. Okay, so you're going to actually have a set that's tied with geometrical spreading and Q.
In fact, I think Gail's going to talk about that a bit in hers as well. These are correlated parameters, and so the stress drop distribution depends if we've got a 1 over R or R to the 1.2 or whatever. So we're going to have separate sets of models for those different conditions. Part of what we need to think about defining during, I think, is it tomorrow? Yeah, the range of parameters is going to be some of those conditions, or what range we want to set up just to get the simulation started so we can see what's coming out. All right, anything else on validation? So keep it simple, is what we're saying. As few parameters as possible, especially for the point source model. I think we shouldn't start the double corner. Right, no. So if there's no other questions, we're going to continue our tradition here of stopping a few minutes early. So we're 7 minutes ahead of time for lunch, and we're back at 1 o'clock.